Okay, we're going to take the same approach here and look at the mass spectrum, then the IR, then the carbon-13 NMR, then the proton NMR. And in the mass spec, first thing I want to find is that molecular ion peak. So in this case, we see that our molecular weight here is 135. And as I see that's an odd number, bells should go off in your head. And right off the bat, you should realize you have nitrogen in your compound. At the very least, you have an odd number of nitrogens, most likely 1. But I can't rule out 3, 5, 7, 9, or any other odd number technically. But we do have nitrogen with an odd number there. And in this case, I'm looking for a peak at 137, and there's no significant peak at 137. So I was looking for an M+2, and it's not really there. So we can rule out chlorine and bromine. So right off the bat, molecular weight, we do have nitrogen, we don't have bromine, we don't have chlorine, move on. So knowing I have nitrogen, I'm also looking, and I see this, and I should realize that down here is where OHs and NHs show up. In this case, that's an NH. And I already knew I had nitrogen, so it kind of corresponds with that. An OH is usually a little broader than that and prettier and smoother. But again, we already knew we had nitrogen, so I was kind of expecting this to begin with. Also, with nitrogen-hydrogen bonds, it's convenient. One peak, one hydrogen attached to your nitrogen. Two peaks, two hydrogens attached to your nitrogen. And so in this case, it's just one peak. So there's just one hydrogen attached to our nitrogen. If we also show we have peaks just left of 3,000 and peaks just to the right of 3,000. And again, that's your sp3ch bonds just to the right and sp2ch bonds just to the left of 3,000. And then working our way down here, and again, usually we'll kind of take 1,500 and ignore everything past that. And we've got a bunch of peaks immediately to the left of 1,500. So the 15 to 1,600 range, that's your aromatic carbon-carbon peaks. So, and this is going to be tricky, and you might not have caught it, but technically, this signal right here is a carbon-oxygen double bond. Now, normally we think those show up at 1,700. This one actually looks like it's closer to 1,600 than 17, so somewhere between 1,600 and 1,650. So it's definitely experiencing some conjugation. We'll find out it's an amide in a little bit, but we'll find out it's even more conjugated than that. But in this case, even if we didn't realize we had a carbon-oxygen double bond from the IR, the carbon-13 NMR would make it very obvious. Let's take a look. So here we've got a signal down here in the alkane region. So, and then we've got 4 signals over here in the 110 to 160 aromatic region, so we got a benzene ring, and then we've got a carbon double bonded oxygen, the only thing that shows up downfield of 160. So again, if we didn't realize we had a carbonyl before with the IR, we definitely couldn't miss it here in our carbon-13 NMR. And yet again, take what we know now and finally spend the most amount of time in our HNMR spectrum. So now let's spend some time looking at the HNMR, and I've summarized our findings from the other 3 spectra. Our molecular weight's 135. We have a nitrogen, and it's bonded to 1 hydrogen. We have a benzene ring, and we have a carbonyl. If we move on here, let's spend some time. We've got a number of signals. We've got 1 down here in the alkane region, and it looks like it's showing up just shy of 3. Maybe it's right next to something electronegative, maybe it's not. But it's definitely in the alkane region. And then we've got all these signals down here that look like they're in the aromatic region. But in this case, I would recommend you find where this H attached to the nitrogen is actually showing up. NHs and OHs can show up just about anywhere, depending on the what molecule they're in, depending on what solvent you're using, things of this sort. So I highly recommend you find them. And NHs and OHs are often broader than most other peaks, and they're typically broad singlets. And in that case, that's this guy right here showing up at 7. So had we not identified him from the get-go, we might have thought he was another aromatic hydrogen. But in this case, he's the NH. He's that broad singlet. So getting him out of the way early is going to help us big time. So that's our NH again. So, and then these other signals, these are the aromatic ones, and they're hard to distinguish, and that's why you're given an expansion here, a blow up of that region. So, and the important thing is not looking at all these signals. The important thing here is first and foremost going to be looking at your integration. So in your integration here, 2 to 1 to 2 ratio, that's a total of 5 hydrogens, and that's super nice. This is your other common aromatic pattern that routinely shows up in an undergraduate class here, and that's a monosubstituted benzene ring here. So we have 1 substituent. The other 5 positions are all going to be hydrogens in all likelihood. So, and whether I analyze all the singlets and doublets and triplets, it's not the most crucial thing in the world. So, but if you look at this thing, there is going to be symmetry here. It's going to reduce the number of signals. It's going to make these 2 H's equivalent. So, and in this case, they're only going to have the 1 neighbor next to them here. So, and as a result, show up as a doublet. So then you've got this guy down here. So, and he's got these 2 neighbors here again. So he would show up with 2 neighbors as a triplet. and then you have these two hydrogens being equivalent. So, and these guys got a neighbor on either side, and they're non-equivalent neighbors, so technically there's some complex splitting on here. But oftentimes the complex splitting on here ends up looking a whole lot like a triplet, even though it's technically a doublet of doublets. But in this case, that's exactly the pattern I see, a 2H doublet, a 1H triplet, and a 2H, something that looks like a triplet, that's technically a doublet of doublets, but we'll talk more about complex splitting later. But that exactly matched our pattern, but whether we realized it matched or not, once you see 5 H's in the aromatic region, so you almost definitely have a monosubstituted benzene ring if you don't have more than one benzene ring anyways. And so in this case, that's what we have, and that's a piece of our puzzle. So we've got the nitrogen here, we've got this carbon here, we've got the benzene ring, so, and then we've got these 3 H's in the alkane region, which again I like, and that's going to be a methyl group. So in this case, that's about all we know. If we kind of take a look here, our methyl group only has 1 bond left to make. It can't go in the middle. It goes on the end of the chain. Our carbonyl has 2 bonds to make. It can go in the middle. Our benzene ring only has 1 bond to make. It can't go in the middle. Has to go at the end of the chain. And then our nitrogen has 2 bonds to make, so it can also go in the middle of the chain. So our 2 fragments that can go in the middle of the chain here, so are the carbonyl and the nitrogen. So we'll attach them to each other. So, and then in this case, the nitrogen also had that hydrogen. And from here, we have 2 options. I can attach the benzene on the left and the methyl on the right, or exactly the opposite. And so we're going to end up with 2 possibilities here. And let's draw both possibilities and see if we can tell the difference. So this is a fairly complicated example here. In this case, I'll start by putting the benzene here and the methyl group here. And in this one, I'll put the methyl on the left and the benzene on the right. See if we could tell the difference here. So if we look, it turns out this is actually the correct structure. It's going to be a little bit subtle, but there's going to be a couple of things that could clue us in. One is the methyl group here, and the methyl group's next to the nitrogen. It's bonded to the nitrogen, which should get it down in the 3 or lower range. And unfortunately, this carbon is just barely below 3, but maybe he's bonded to the nitrogen. I'm going to say that he is. The alternative would be having it next to the carbonyl, and having it next to the carbonyl might get it around like 2.2, 2.3 typically. So odds are it actually is, again, that first structure based on the position of where the methyl group's shifting in the H NMR spectrum. The second thing we could do, though, is if you recall, the carbonyl peak in the IR was showing up somewhere way down at like 1640, maybe even 1630, but definitely below 1650. A normal amide is conjugated with the lone pair of electrons on the nitrogen. It typically shows up in the 1670, 1685 region. So in this case, this is even more conjugated than that. And the reason is this is also conjugated with our benzene ring. Notice double, single, double. It's conjugated with all the pi electrons in the benzene ring. That additional conjugation lowers the stretching frequency of our carbonyl even further, explaining why it's at 1640. In our other molecule, our carbonyl would be conjugated with the lone pair on the nitrogen, again, maybe causing it to shift maybe 1670 to 1685, somewhere in there, but it's not conjugated with the benzene ring. It's attached to the methyl group over here, and wouldn't see any further conjugation, so we'd expect it to show up somewhere closer to like 16, maybe 70 at the lowest, but definitely not 1640. So again, the difference between these two is a little bit subtle. Most of the time, if you got this on a test, if you got this wrong choice on the lower left, you'd probably get most of the points, but the one on the top right is definitely correct. It's a little subtle, the distinguishments, but it is things you have technically learned.